Hello everyone, my name is Feng and I'm currently a postdoc at Carleton University in Ottawa, Canada. Today I'll be presenting our paper titled Subjective and Objective Evaluation of Procedurally Generated Audio for Sound-Body Interactions. Traditionally, sound synthesis for computer animations and games is done by a method called Foley, which puts audio effects manually to a scene during post-production. This method can produce fine-tuned results, but require a lot of human efforts, so it's not ideal for complex interactions such as sound bodies. As a result, recent advancements in computer-assisted techniques have motivated the synthesis of more complex sound using procedure generation. These methods typically generate audio by running a predefined program, which makes the process fully automatic. However, they lack standard evaluation criteria to validate and control the output quality. Therefore, the motivation behind our research is to explore practical evaluation criteria to assess the performance of procedurally generated audio, specifically for complex interactions such as sound bodies. We aim to look at subjective evaluation, where we seek to explore the recognizability, quality, and synchronization of synthesized sounds. We also want to investigate objective evaluation, where we seek to measure the recognizability and similarity of simulated sounds, as well as compare these results to subjective ones. Alright, so here are some backgrounds. Generally, for procedure audio generation techniques, there are 4 groups of methods in previous works, which can be categorized into physically based and data-driven approach. Physically based methods are typically used for producing rigid body sounds. In the case of soft bodies, most synthesis methods take the data-driven approach, which creates new sound textures from characteristics of recorded audio. The top 2 most commonly used methods are granular synthesis and concatenative sound synthesis, or CSS. So in this research, we'll be focusing on evaluating the synthesized results from these 2 methods. In terms of sound evaluation techniques, normally for rigid bodies, this is done by comparing the spectrogram or using perceptual user studies. There are also several objective metrics such as error rate and signal-to-noise ratio to measure the quantitative properties. However, as sound body sounds usually have no common structures, these metrics won't be very effective. To find a viable solution, we look at using deep learning technologies such as the inception score, or IS, and Frechet inception distance, or FID, borrowed from the assessment of generative adversarial network, which can precisely capture the characteristics of the audio. For subjective evaluation, we conduct 3 user studies to assess the recognizability, quality, and synchronization of our audio. A total of 25 subjects participated in our study. The stimuli include 3 groups and 12 categories of recorded and synthesized sounds, where Group 1 contains the results produced from granular synthesis, and Group 2 and 3 are based on CSS with different variations. The entire study takes about 90 minutes to finish. For Study A, we assess the recognizability of the audio, where we play a clip like this. And ask the subjects to select which image best matches the sound and rate its realism. In Study B, we evaluate the quality of the synthesized sound compared to the recorded one, where we play 2 clips side by side in random order, such as this. And participants are asked to rate which audio clip they prefer. Finally, Study C verifies the synchronization of the results, where we play a video clip like this. and ask each subject to detect any asynchrony between audio and visual and rank their naturalness. For objective evaluation, we propose two metrics based on the concept of IS and FID. To set up our experiment, the first step is to retrain a CNN with a large audio training set to ensure that the network can work well with extracted audio features. So we use the Urban Sound 8K dataset and convert all audio into mono signals. Then we divide each signal into short segments with overlaps and transform them into Mel spectrograms to represent the audio features. Next, we save these features as RGB images to form the input to the network. Finally, we take a pre-trained CNN called GoogleNet, replace the last two layers, and retrain it for 12 hours with our new input. As a result, the modified GoogleNet can achieve an accuracy over 88%. To calculate the IS of our audio, we first train the modified GoogleNet on a separate salt-body dataset, where we get a new inception network that has high accuracy and can classify 12 classes of salt-body interactions. Next, given any recorded or synthesized stimuli, we apply it to the new network to determine its conditional probability. We then assume a uniform marginal probability so that we can calculate the KR divergence between the two, and the exponent of the results will be the IS of our input audio. With this score, if our input clearly sounds like one of the 12 classes, the resulting IS would be high. On the contrary, if the audio quality is poor, then we would have a low IS. We also introduced the FID to measure the similarity of our synthesized sounds to recorded ones. Given both recorded and simulated audio, we use the last pooling layer of the inception network to calculate the feature vectors of both sounds. The FID can then be computed as the Frischette distance between these two features using this equation. Consequently, if our simulated audio is similar to the recorded one, we would have a low FID score. Otherwise, the FID would be high. Okay, so here are the subjective evaluation results. For recognizability, the overall accuracies for both simulated and recorded audio are fairly close. In terms of realism, we also get a very close score. To further analyze these results, we perform several ANOVA tests and find no significant difference between these two sounds. For the quality evaluation, our mean preference score shows that the subjects perceived all simulated sounds to be similar to the real recordings, which correlates well with our objective measurements using FID. As for synchronization, our human evaluation shows that all simulated audio has achieved a good level of synchronization as well as naturalness. Moreover, we find a strong and positive correlation between these two data, which means that highly synchronized sound can improve the audiovisual experience. And here are the results of objective evaluation. We calculate the IS for both simulated and recorded sounds and find no significant difference between them. We also compare these data with our human evaluation. Unfortunately, no correlation is found. Similarly, we compute and normalize the FID scores between our simulated and recorded audio. This time, we find a significant and positive correlation between FID and our subjective evaluation. So to summarize, here are a few interesting findings. For recognizability, some subjects have reported difficulty in differentiating between sounds, such as cotton and polyester cloths. So this may help improving the computational efficiency by using, say, one type of cloth audio to generate other sounds that are perceptually similar. For quality, we found that continuous sounds, such as hand rubbing, tend to yield larger difference between simulated and recorded audio, which suggests that longer sound segments are needed during synthesis to preserve more temporal information. Finally, for synchronization, simply adding synchronized audio does not always lead to improved realism for procedural audio. Sometimes trade-offs are needed for better overall fidelity. In terms of different evaluation criteria, although subjective study is still effective, it requires a lot of time and effort and may be subject to possible judgment biases. In contrast, objective metrics are much faster, more accurate for performance evaluations, and when combined with proper psychoacoustic principles, it can be more efficient. Additionally, we find that IS does not correlate with human data, so should only be used as a rough guide, whereas FID is more effective and has a huge potential. For future directions, we'd like to expand our metrics to include more sound phenomena and explore other potential methods in the field of image processing. We also want to make several improvements, such as building larger datasets and deeper CNNs. Finally, we'll try to integrate the FID matrix as part of the workflow for audio synthesis in commercial engines. And that concludes my presentation. Thank you very much.